Hello, my name is Helen Urgelles. I'm a telecommunication engineer with a master's degree also in telecommunication, and I recently got my PhD, which was about quantum computing for future wireless communications for beyond 5G networks, with a special or particular focus on 6G. And today I would like to share with you my investigation throughout the past years. Okay, so the table of contents of this talk will be will start with the introduction and objective of the investigation. Then I will comment very quickly the quantum computing fundamentals. After that, I will provide the main contribution of the investigation, that was quantum enhanced interlocalization, quantum routing optimization, quantum maximum likelihood detection for MIMO and NOMA systems. And finally, I will comment very quickly the relationship between quantum computing and the Sustainable Development Goals from United Nations. And at the end, the list of publications that I did during my PhD. Okay, so mobile communications have evolved dramatically over the last 4 decades. From the first generation that only supports voice calls, we have progressed to the fifth generation, which supports Internet of Things, autonomous vehicles, augmented reality, among others amazing applications. However, despite this advance, 6G, 5G, sorry, is expected to face in the future some limitations in latency, energy efficiency, and global coverage. For that reason, and projected for around 2030, 6G, the next generation of mobile communication, will seek to unify the physical, digital, and human worlds with unmatched speed, intelligence, and connectivity, enabling everything from immersive experience to digital twin applications. To make this vision concrete, 6G is expected to rely beyond the technical key performance indicators, such as a high terabit per second data rates, or a high global coverage, or high energy efficiency. It's expected that this technology will be aligned also with some values, key values indicators, such as sustainability, scalability, digital inclusion, and trustworthiness. This technology will allow a wide variety of use cases. For example, smart cities, immersive healthcare, also in Industry 4.0, autonomous mobility, and so on. But these demanding scenarios require or will require fundamentally enablers technologies and new approaches to computation, such as multi-band utilization, heterogeneous networks, integrating sensing and communications, intelligent, secure, and green communications, and the new one, quantum computing. But how integrate quantum computing in future wireless network? So that was the reason of my PhD, my investigation, with an overall goal of explore the principles and latest advances in quantum computing to identify solutions for future 6G communications. And most important, bridge the gap between theory and practice in this field. This main goal was then divided into 4 specific ones. First, conducting a comprehensive review of quantum computing for 6G applications, analyzing and selecting appropriate tools like IBM and Qiskit, proposing suitable candidate applications, and designing practical implementations of applications that serve as proof of concepts, paving the way for future use of quantum technologies in mobile communication networks. So integrating quantum technologies into future wireless networks will represent a profound paradigm shift, especially for the proliferation of the fields of quantum communications, quantum computation, quantum networks, and quantum machine learning. For example, in non-terrestrial networks, satellites and drones, um, radio access networks, data centers, or in blockchain integration throughout quantum cryptography. These are some areas where quantum technologies can provide some advantages. On the other hand, um, through an extensive review, other areas were also identified that weren't explored at the time when I began this investigation. That was in the localization, routing optimization, in signal detection, the maximum likelihood detector, and how to integrate or how to integrate the quantum computing with the sustainable development goals from the United Union that are also projected for 2030. So, um, why uh, why even consider quantum computing for future wireless networks? Well, if we can ask Richard Feynman again, maybe he would likely say that because nature is not classical from his physics point of view. But if we ask our new friend, we can get that quantum computers are appealing because they expand the type of problem that can be tackled efficiently, among others answers. But what is real is that quantum computing is a new way of processing information. It's a new way of computation that there is based on quantum mechanics. Hence, the postulates of quantum mechanics provide the mathematical and physical rules. For example, unlike classical bits that is restricted to the state 0 or 1, a qubit is a two-dimensional vector in a Hilbert space that is represented as a linear combination of 0 and 1 states, where alpha and beta are complex amplitudes, and depending on their values, the qubit is more likely to be 0 or 1. And it's represented as a block sphere that we can see in the slide. Also, the evolution postulate that is represented or that is represented by the Schrödinger equation in quantum mechanics. It's related to the unitary quantum gate in quantum computing. The measurement that is the last step in quantum computation allow us to get the classical the classical bit with certain probabilities, and the measurement in quantum mechanics collapse the superposition of the quantum state. Others important or other main features of quantum computing are superposition, but I already mentioned it, entanglement, quantum tunneling, and the wave particle duality. But the point here is that we are presently in the second quantum revolution, because we are not only observing quantum effects, we are actually engineering them to process information. In this regard, this figure represents or summarizes the quantum computing platform classification available. For example, classical computers that include quantum-inspired and quantum emulators, analog quantum computers that include quantum annealing and quantum simulator, and the universal quantum computers that is divided into the noise intermediate scale quantum that is where we are today nowadays, and the large scale quantum computers, the quantum computers in the future. And throughout this investigation, the IBM quantum platform, Qiskit, was used to develop the application, the proposed applications. Okay, so I will start now with the first contribution of the investigation that was quantum enhanced indoor localization. Indoor localization is related to determine the position of a new user or point inside a room, and the technologies used to do it to determine the position are, for example, Wi-Fi, Zigbee, 5G, and among others. And the main metrics to measure are the received signal strength indicator, time of flight, time, angle of arrival, channel state information, and others. In this regard, quantum computing could boost accuracy, efficiency, and scalability according to literature. However, when I began this investigation, the lack of a complete quantum distance framework motivates us to propose the quantum fingerprinting algorithm based on the Euclidean distance but calculated uh, by a quantum computer. The methodology followed was the proposed in the slide. Firstly, a measurement campaign, then the how to calculate the Euclidean distance by a quantum hardware, a hierarchical refinement sample, and finally some advantages about the approach. The first step, that is the measurement campaign, is an offline step where the target area is divided into tiles, and each midpoint of the tile is taken as a reference point to populate a database with the received signal strength indicator or any other parameter from all of the access points around or antennas around the room. Then in the online step, when a new device or user uh, comes into the area, the target area, the distance, the distance between the values of the new user and the previous stored is calculated by the Euclidean distance, but in quantum version of the Euclidean distance. Obviously, small tiles mean higher accuracy, but this will represent a larger database. So the Euclidean distance in classical computing is just a straightforward vector subtraction. However, when we move into quantum domain, it's not in that way how it's calculated. To calculate the Euclidean distance or to get the Euclidean distance in the quantum domain, it's we can use the overlap between between two quantum states. And now I will explain how to do it following this pipeline. Starting from the data preparation, that is where we encode the classical data into quantum state, then the quantum circuit construction that allow us to calculate the distance or the similarity between quantum states, then the measurement, and after the measurement, we then calculate the distance. We can then calculate the distance according to the measurement. So the first step, that is encode, that is to encode the classical data into the quantum domain, can be done with or throughout many ways. For example, basis embedding, angle embedding, amplitude embedding, among others. That is a feature map. The quantum embedding that I used at that time was the amplitude embedding. That what it does, it normalizes the data, the classical data, dividing by the norm of the vector. So, for example, if we have the real time parameter from the new point in the room, and one of the stored values, we divide the vectors by their norm, and then we can obtain the quantum states. So once we have once we have the quantum state, the classical data encoded into quantum state, the next step is to figure out how similar or different those states are. And this similarity can be calculated by this vector on this operator, sorry, this quantum operator on the slide, where we have the two quantum states and the and Hadamard gates and swap test operator. The way to get the similarity between the overlap between the quantum states is measuring the auxiliary qubit, where we have the Hadamard gate. So when we measure this auxiliary qubit, this ancilla qubit in the zero state, if this probability of the auxiliary qubit in the zero state is close to 1, it means that the quantum states are identical. Otherwise, if the probability of the auxiliary qubit in the zero state is close to 0.5, it means that the quantum states are orthogonal or very different. So it's just an inner product between the quantum state by calculating through this operator here. Then with some mathematical relationship, we can get the quantum Euclidean distance that is shown also in the slide on the right. So an example of this approach is it's presented in this slide. For example, let's imagine that we have a square room, a square office, or whatever, and the target area is divided into 4 tiles. The midpoint of each tile, that is represented as A, B, C, and D, are used to populate the database that is shown in the table, where the reference signal strength indicator values are previously saved. Then, when a new user, in this case that is represented as R, comes into the room, the distance, the location of this new user is calculated or is determined by the quantum Euclidean distance. And the main advantage of this approach is that the distance between the new point and the previously stored one can be done in parallel. From the first iteration, we get that the new vector, the new value, or the new user is in the first square A. Then in a second iteration, this square is divided into 4 more tails, and this process can be repeated until the desired accuracy is obtained. So some advantages of this proposal is the way of calculating the quantum Euclidean distance in parallel. Obviously, we need to have a lot of qubit to do it. And it's represented by the second step here. After having the classical data into quantum state, we can get the quantum Euclidean distance calculation throughout the superposition and the parallel comparison of the quantum state. After that, we measure the auxiliary qubit and we make the decision based on the results of the Euclidean distance. Here are some results about the first iteration that were obtained from one of the IBM quantum hardware at the time I started. I think it was like, well, it's in the slide, IBM Casablanca and IBM Melbourne. And the graph on the left represents the relative error versus the number of shots, where a shot is one full circuit run and measurement. At that time, the number of shots to get less error was very, very high. Around 4,000 shots were needed to get the first results of the Euclidean distance calculation. And on the right, we have a comparison between a classical and a quantum computer in terms of the time required to compute the Euclidean distance. Obviously, some of the results are some estimations. Maybe we were very optimistic, and it's based on the vector length of the vector length. And of course, if we have more qubits, we can calculate this distance with a higher vector dimensions. And the key point here is that at some point, we don't know when, the the quantum computing, the quantum computer can outperform the classical one. Okay, so the second contribution of the investigation was quantum routine optimization, because in future, actually now we are in this scenario, but in the future, in 6G or even other network technology, the network will be ultra dense, and the one of the key challenges will be the routine optimization. I mean, how to design algorithm that allow the information goes through the network, while, for example, maximizing throughput and minimizing cost and minimizing latency and so on. At this point, one of the quantum algorithm that can be used to to perform the quantum routing optimization is the variational quantum algorithm, because it's a hybrid approach that is based on a classical optimizer and a parameterized quantum circuit, and is suitable for to today's noisy intermediate scale quantum hardware. And the main point is that the optimization problem, in this case the routine network optimization problem, is encoded as a Hamiltonian, which is a core concept inside the variational quantum algorithms. If we encode the optimization problem as a Hamiltonian and we find its ground state, we can obtain the optimal solution of the problem. The Hamiltonian in quantum mechanics represents the total energy of a system. So um, I will repeat this again because this is important. We have on the one hand the Hamiltonian that represents the total energy of a system in a quantum computer, and on the other hand we have a problem, a routine problem in a network optimization, in a wireless network, and we want to optimize this network. So if we represent the network as a Hamiltonian, and we get the ground state of the Hamiltonian, we obtain the optimal solution. So the algorithm used inside the variational quantum algorithms was the quantum approximate optimization algorithm, because it can tackle NP-hard problems. It's an approximation approach. It's variational because it's based on a classical optimizer and a parameterized quantum circuit, and it guarantees a good performance even in today's noisy hardware. So here is a summary. It's a summary of the QAA operation principle, where first we define the Hamiltonian that is divided into the cost Hamiltonian that encodes the optimization problem, and the mixer Hamiltonian that allows the algorithm to explore the search space. Then based on the Hamiltonian, we can build a quantum circuit. And if the Hamiltonian is repeated in many layers, the algorithm the algorithm can improve the solution. We prepare the initial state in the superposition of through Hadamard gate, and then we optimize the parameters classically using Adam, Covilla, or any other classical optimizer. And this is repeated until the Hamiltonian is in the ground state that is the optimal solution. So the methodology to develop the quantum routine optimization it's represented in this way. First, we have the problem representation. If we have a network, we need to represent it as a directed graph. Then the QO formulation to solve the problem by a quantum hardware. Then trying to find the Hamiltonian, build the quantum circuit, and finally the optimization and get the solution. Okay, this simple example that was developed on IBM quantum hardware years ago, maybe in 2022, with a few qubits, 5 qubits or something like that. It represents a network with 4 nodes. The node 1, the source, and the node 4, the destination one. And the weighted in the and the weights in the edge represents the some network parameters, for example, cost, throughput, and so on. The problem representation in this case very clear and simple because it has only 4 nodes. Some constraints are add to the problem because it's in that way we can ensure the functionality of the network. For example, the flow conservation between the middle the middle nodes. Then once we have the problem representation, we need to figure out how to solve the problem by the quantum hardware. In this case, how to mm, build the Hamiltonian. To do it, the QO, the quadratic and constrained binary optimization, allow us to determine this to build this Hamiltonian. So the optimization problem formulation is represented as QO, adding some penalty and in some penalty to make the function unconstrained, and then this allow us to get the Q. After expanding this expression here, we can obtain the Q, that is a square matrix of quadratic coefficient, and the C vector of linear coefficients. And having these two, the Q matrix and the C vector, we can obtain the Hamiltonian, the cos Hamiltonian of the problem that contain this matrix and the vector. And with some transformations, we obtain this the cos Hamiltonian based on identity gate and Pauli zeta gate. And also we have the mixed Hamiltonian that is represented by Pauli X operators. Here we have the example of the circuit for the single objective quantum routing optimization that starts from the Hadamard gate that allow us the superposition, then the Hamiltonian that is represented by the Cox Hamiltonian, which rotational zeta and zeta gates that allow us to make entanglement between the qubit that represent the path between the nodes in the network, and then the mixed Hamiltonian that is represented by Pauli X operators. Finally, to obtain the solution, Povila was used as a classical optimizer. This was executed on IBM Perth that now is deprecated. And the optimal parameter of the circuit was the parameterized quantum circuit was those that are shown in the slide. And on the left, sorry, we have the probability distribution of the possible bit string, and the circled one is that one that corresponds to the optimal solution of the problem. On the right, some example that if we increase the layer of the Hamiltonians the layers of QoA, we can obtain a more accurate result. But also this comes with some effect that we have a more a deeper circuit, so we can get more errors in the results. Also, some multi-objective routing optimization was done and published in some papers using the lexicographic methods to obtain the Pareto optimal, the Pareto front, to for example, to maximize the throughput in a network while minimizing cost and, for example, to save battery life. Here is the example of this lexicographic method, where the idea is actually very simple, because the objective is ordered by priority. So, for example, if you want first to minimize the battery cost, and then maximizing the throughput, and finally minimize the hop, the jump between the source and destination, we can formulate the problem like this. For example, firstly minimizing the cost, then this is added to the second objective, so to the second to the second optimization problem, using some slack parameters that allows the methods, the algorithm, to solve the problem without broke broken the previous path. So if we maximize the throughput, we can do it, but without affecting at all the cost previously obtained. And here we have some results about time versus clocks, where clocks are circuit layer operation per second. And so, for example, at that time, around 2022, some hardware were tested in this regard. And for example, if we see uh, Belém and Quito with 5 qubits and less clocks, less values of clocks, they outperform, for example, Lagos with higher qubits, or Lima and Manila with the same number of qubits but higher clocks. So what it means that in the case of quantum hardware, we need to take into account not only the clocks. For example, we need to take into account the quantum volume, the number of qubits, how they are interconnected, and the fidelity of the gate, and so on. On the right, some estimation that were done at that time. At that time, we were in the red band, for example, with 5 7 qubits. Now we are in the yellow one, and maybe in the future, the green region, where the quantum hardware can outperform the classical one regarding the routine optimization, where the number of nodes increase enough. And now, finally, it's not the final, but one of the final, one of the last contribution of the investigation, that is quantum maximum likelihood detection for MIMO and NOMA systems. In mobile communications, MIMO is one of the key technologies nowadays, because it allows a higher spectral efficiency and throughput, using multiple antennas at the transmitter and multiple antennas at the receiver. And NOMA, on the other hand, that is non-orthogonal multiple access, allows the user to share the same frequency and time resources. So when we combine the MIMO and NOMA systems, this combination allow us to get a higher quality of service, higher spectral efficiency, and throughput. However, the challenge is in the signal detection, because with a lot of users, the the signal detection becomes a complex problem. In this regard, the maximum likelihood detector gives optimal performance, because it evaluates all possible transmitted signals. What it does is a search, a exhaustive search allowed through the transmitted signals to get the most optimal one. But when the number of users increase, the complexity of the problem also increase. And in this case, quantum computing, because the maximum likelihood detector becomes a combinatorial optimization problem. In this regard, quantum computing can improve this estimation, this detector. So the methodology followed to solve the maximum likelihood detection by quantum computer is very similar to the previous one, the quantum routing optimization, because as the maximum likelihood detector is a combinatorial optimization problem, the variational quantum algorithms and QAOA can be used to solve it. So we have first the problem representation, then the QO formulation, the quantum encoding to obtain the Hamiltonian, the quantum circuit construction according to the Hamiltonian, and finally the optimization and solutions. Okay, so MIMO and NOMA can be done in a downlink or uplink communications. Uplink communication is from the users to the base station, and the base station performs the signal detection, and the downlink is the other way around, where the base station send the information to the users, and they perform the signal detection. In this case, this example is based on the uplink communication, where the signal received is represented by Y on the left in the slide, and H represent the channel metrics in a MIMO systems, and alpha represents the power allocated, the power allocation according to NOMA, because in NOMA the users are the users are assigned with some power allocation depending on the distance between the user and the base station. So the maximum likelihood detector in my monoma system is represented by S, where is where the point is to minimize the distance between the received signal and the transmitted one. And the example proposed is a MIMO and NOMA system with two users, or what is the same, two antennas at the transmitter and two antennas at the receiver. Assuming the binary phase shifts keying modulation with is actually the simplest one in communication. And so with these assumptions, we can get the problem optimization, which is the minimization of this, and obtain then after expanding this expression in the middle, we can obtain the QO formulation to get the Q matrix and the L vector that represent the linear coefficients. With the QO formulation, then we can get the Hamiltonian, the cost Hamiltonian, and the mixer Hamiltonian, and build the quantum circuit. So some results are presented here in the slide for 1000 bits transmitted and 10,000 bits transmitted. The point here is to note that the quantum approach actually behaves like the classical ones in terms of the bit error rate between versus the transmitted power. Obviously, for example, for 10,000 bit transmitter, the similarity between the classical and quantum approaches are better. They are more similar because we send more bits. Then also a MIMO and NOMA system with a higher order, 4x4, was also implemented. And these are the results and the way of the Q and L from the QO formulation were done, the Q metrics and the L vectors. The distance, the D and alpha are the distance and the power allocations according to NOMA systems, and the graph represents the results of bit error rate versus the power transmitter for both the classical approach, the classical maximum likelihood detector, and the quantum maximum likelihood detector. And finally, I will comment very quickly about the relationship between the quantum computing and the sustainable development goal from United Union. And this is the last contribution of my thesis that was actually published in a paper called In Network Quantum Computing for Future XG Network. The main message here is that most quantum computing research focuses on speed and performance, but hardly ever about the cost or the social impact of these systems. I commented at the beginning of the presentation that it is expected that XG should not only look at the classical key performance indicators like latency or spectral efficiency, but it should also include key values indicators such as sustainability, scalability, and trustworthiness that are aligned with the United Nations Sustainable Development Goals. And in this work, we connect today's quantum hardware features like efficiency, temperature, and the coherence to those XG values. And this helps us to see where quantum computing can truly help fusion networks and where it might still pose challenges, for example, in energy consumption or cooling needs. So the idea in the future is to build a balanced roadmap, one that makes quantum computing part of a sustainable development future. And finally, well, these are the reference that actually are the paper that I could publish throughout the investigation, throughout my thesis, that are 3 journal papers regarding the quantum routing optimization, the the one that I mentioned before, the in network quantum computing for future CG network that relates the sustainable development goals with quantum computing, and the quantum-based maximum likelihood detection in my monoma. Also two conference paper and some related works that was a master thesis and a post in Qiskit medium that it was how to calculate the Euclidean distance using Qiskit. And that's it. That's all from my side. Thank you. Thank you very much.